So we did the locker problem. We did the locker problem last week, Thursday and Friday. And I said one of the longest problems or questions that was going to take you the longest time to answer was this first question. So our goal was to determine at the end of all 100 numbers, which lockers would be left open. Gus, do you have a list?
Yes.
All right.
1, 4, 9.
Oh, hang on.
1, 4, and 9.
Okay.
16, 25, 36, 49, 64, 81, and 100.
All right. So that is 10 lockers, and those are the correct 10 lockers. Okay, did anyone else have that set of 10 numbers listed as the lockers that were open? Cammie, yes. Anyone else? Okay, so Gus, tell us, how did you determine that those particular lockers would be open?
So there are two ways to figure this out, but one way I did it, I did like the first 20 or 30 numbers, and I noticed like a little pattern with all the markings. Between 1 and 4, there are 2 marks, but between 4 and 9 marks, there are 4 marks. And every time you start marking numbers, it goes up by 2. So 1, 2, 3, those are 2 marks, they're both closed. Then 4. Then you do 4 marks for all the closed ones, then 9, and then you do 6 and 8, and then so on. And
Okay.
then I got the right answer. And then there's another
Okay,
step.
hang on. Hold your thought because I want to explain that. Go ahead, Weston. So if you're not sure what Gus is referring to as the marks, what he's talking about is on the back, how you had that 100 numbers grid. In his clear board, when he marked the ones that were closed, he was saying, here is locker 1, which was open. The next open locker was 4. There were 2 closed ones in between. And then between the next 2, there were 4 closed ones. And then there were 6 closed ones. Same idea as what somebody first period said, but they looked at it this way. They said, well, to get from 1 to 4, I needed to add 3. And then to get from 4 to 9, I needed to add 5. And then from 9 to 16, I needed to add 7. Then plus 9. This one was plus 11. So you are adding 2 more to the previous what you added that last time. Okay? So that would be, if you had figured this out, your explanation in the second question. How did you figure this out looking at the pattern? What, though, do we notice about those particular numbers, which I think, Gus, is probably your second observation, yes?
They are all square numbers.
These are all square numbers. Who can explain to us what Gus means by the fact that these numbers are all square numbers? Who can explain to us what that means? Anaya.
So basically a square number is like a number times itself.
It's the result of multiplying a number by itself. So 1 is 1 squared. 1 times 1. We have 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, 6, 7, 8, 9, and 10 squared. Very good. So those are all square numbers. That was the observation we were hoping to land on if you figured this out. Okay? Well, now is the analysis part. Okay, great. It was the square numbers that were those numbers that were all open. The question, though, is why? So I'm going to give you a second to think about this. I know you've got this. I want other people to have the opportunity. Why? What's unique or different about square numbers that resulted in those ones being open, but no other lockers being open? Okay, let's talk through this for a second. We could just give you the answer, or have Gus explain why he thinks the square numbers are open, but I don't want that. Let's see if we can problem solve this. So you don't have to write this down, but let's think about this. Locker number 10, for example. Who would have opened or closed locker number 10? Give me the numbers that would have opened or closed locker 10. Bless you. Bless you. Liv. 2, 5, 10, and 1. 1 is the first person. So 1 came in, opened it, 2 closed it, 5 opened it, 10 closed it. What about locker number 18? Nope, I don't like that number. What about locker number 5?
50.
Oh, sorry. 5. Who came in and opened or closed 5? Come on. Use your brains. You can do this. Some of you are sitting there like bumps on a log. Let's think this through. You can do this. Who touched 5? So, who touched 5? 1 and 5. Who touched 12? That's what I was going for. Griffin.
6 and
12. 2. 4. What are we listing? The what, Jonah? The factors. So all of the factors of that number were the people that came in and opened and closed that locker, right? Well, why is it then that the square numbers, so let's take 16 for example, was an open one. We would have 1 and 16 as our factors, 2 and 8. What else? 4 and 4. Oh, but 4 is just... What's unique about the square numbers and who touched those square numbers that caused them to be open at the end compared to these other ones that were not square?
Just let Gus have it.
No.
Why? You've had 3 other people in it.
Let's go with the observations. That is a good observation. 16, all the factors are even. That's not why, but that is a great observation. Liv.
All the ones that are the factors and the ones that are not square, they are all even numbers.
Not 5.
No, there's 5 has 2 factors.
They have an even number of factors. Is that what you were trying to say or no? You were saying something. Okay. So 5, 10, and 12 all have an even number of factors. What do we know about 16?
It has an odd number.
It has an odd number of factors. Why does it have an odd number of factors?
Because it's a prime number.
No, it's not. 16 is not prime.
Because it's a square number. Whoopsie.
What does that mean? Why is there an odd number of factors in a square numbers?
Because it's something times itself.
It's something times itself. That 4 is not going to be written up there twice as a factor 2 times. So in these other non-square numbers, the factor pairs essentially cancel each other out. 1 opens it, but it's got this counterpart that cancels out the opening. 1 opens it, 5 closes it. 1 opens it,
10 closes it.
well, essentially 2 closes it next, but you see how they match up? Here, 1 opens, 2 closes, 4 opens, 4 doesn't then close it, 2, just because it's 4 times 4, it's only going to do one thing to it. So because the square numbers has that double factor in it, it ends up with an odd number of factors, and there's nobody to cancel that other piece out, okay? Did anyone pick up on the fact, before we jump back over, do you remember the first day we started this, I wrote on the board the first 10 numbers? And I said, we'll just start something small. 1 came in and opened all of them. 2 is going to close every second locker. 3 comes in and changes every third locker. So they're going to open this guy. They're going to close this guy. 4 comes in and changes every fourth locker. So they're going to reopen 4 and 8. 5 comes in and changes 5 and then opens 10. Did anyone pick up on the fact that, okay, I just went through the first 5. Once I get through the first 5, what do we know about these 5 lockers?
Yes, repeat it.
Those are just going to stay the same.
Is anyone else going to come through and touch those first 5 lockers?
No.
So once I get past 6, is anyone going to come in and touch the first 6?
No.
Once I get past 10, is anyone going to touch the first 10?
No.
No, so I could have just done the first 10, and then once I get through the first 10, I know what those 10 are going to look like. And I would have had 3 of those numbers already, because nobody after 10 is going to touch the first 10. Did anyone notice that or kind of tune into that when you were doing this? Okay, so that's something that would have been a great observation to make. Okay, so if we look at this fourth question, why are these specific locker numbers still open? They're still open because they had an odd number of factors. They had an odd number of factors which caused them to not get kind of canceled out there at the end. Okay, all right, next question. This is kind of shifting gears. How many lockers and which ones, we're not going to list which ones, but how many lockers, or I guess I take that back. I want to know which ones, not which specific numbers, what types of numbers were touched exactly twice. Anyone have a guess? So if we're thinking about the fact that the factors are the numbers that touched each locker, which types of lockers would have only been opened or closed twice? Miriam?
So I know that the numbers that like have like 6, like 6, 30, like 6, 16, 26, 36, and so on. Like 6 has been touched.
For twice? So if I think of locker 6, I would have 1 and 6, 2 and 3. That got touched 4 times. So it's not 6s. Blake? Okay, so 5 was an example of one that was only touched twice, 1 and 5. What do we know about 5? Does it fall into a category of some sort? It is odd, but it's a prime number. What do we know about prime numbers?
They don't have any factors.
Their only factors are 1 in themselves. They only have 2 factors. So the lockers that were only touched twice would be any prime number lockers because they only have 2 factors.
One would touch it and then touch it.
Correct. All right, what about the next one? Which students touched both 36 and 48? Who's the first person that touched 36 and 48?
2. 1.
1. Then who?
2.
Who else?
4. 3.
3, 4, 6.
No, not 8. 12.
12. What are we listing? We're listing the what of 36 and 48. Ooh, be more specific. Not just the common factors. We're listing all of the common factors. So whatever factors they had in common touched both of them. Okay? All right. Last question was a bit of a challenge. I'm not sure anyone got this far or got this one right. There were actually 2 lockers that were switched the most times. What's wrong? Which 2 lockers? Anyone have a guess? Some people said, 100's the highest number, so it was touched the most. It had nothing to do with what the highest number was. We're essentially looking between 1 and 100. Which number has the most factors? Anyone know?
I have a guess this time.
Okay.
I think it would be 96.
96 is one of them.
96 has like 12-ish, 10-ish factors.
Okay.
And it has like one of the most factors.
It does have the most factors.
Second number would be 84.
Not in the 80s. 96 and Liv?
25.
Ooh, higher than 25.
I'm trying to throw one out there, 32.
Higher than 32.
56.
Higher than 56.
78.
Ooh, super close. It is in the 70s, but it's not 78. Jonah?
75.
Lower than 75. Ella?
72.
72. 72 and 96. That was a hard question if you didn't start listing out factors of numbers. That was going to be a hard one to solve, but those 2 would be touched the most because they had the greatest number of factors. Okay?
They both have one factor. They both have, I think, the greatest common factor.
Since we continue to find pee on the toilet seats, I put together a compilation of a few just reminders and how I feel about walking into the bathroom with pee on the toilet seat. So let's talk about this. Here are some of... Or like that you forget to flush the toilet too. Like, yes, they're automatic, but if it doesn't automatically do it before you walk out, we do know that there's a little button on the side you can push to make it flush, yeah? Okay. So carrying on, here we are. This is generally like what my face looks like when I walk into the stall and I see that I have to wipe pee off the seat before I can go to the bathroom. So, yeah.
That's why like the girls' bathroom is never in there.
Yeah, I'm going to go ahead and assume that it's probably a problem downstairs too. Just because you're using a different bathroom doesn't mean that people stop being on the seats. So we're all going to work together on this one, you guys. And in case you're confused, I put together, or I found a little diagram for you. You're aiming for the hole in the middle of the toilet bowl. That's what you're aiming for. Okay? Yeah? If you feel like you need to start walking out of the bathroom like this to show us your victory, like I walked out and I didn't pee on the seat, you do it, okay?
How did they get
But
that picture?
here we go. I have an 8-year-old son at home. He's in 3rd grade and he knows a couple of basic rules. So I'm going to remind you of the same basic rules my 8-year-old knows. Boys, when you go to the bathroom, lift up that toilet seat, pee, and then when you're done, put the toilet seat back down. This is me being a mom and telling you how to do this. Girls, sit, pee, stand up, okay? If either of you, I don't care what gender you are, I don't care if it's Rutledge and he realizes he peed on the toilet seat because he was here at first period when I gave this. If you get up before you walk out of that stall and you notice, oopsies, I made a mistake. My 8-year-old knows this. Sometimes it happens. You aim for that giant hole in the middle and oops, I accidentally missed and it's on the seat. You're going to go ahead and take some toilet paper out and wipe your own pee off the toilet seat so that the next person doesn't have to do it for you. Go ahead and toss that toilet paper in and give it a little flusheroo. And then most importantly, when you come out, you wash your hands. Ugh. I'm telling you that if at my house, my 8-year-old knows that if he accidentally pees on the seat, he needs to wipe it up and flush and wash his hands, that you as 6th graders and middle schoolers can handle that same expectation. Okay?
I've never experienced either.
Thank you for coming to my TED Talk. I'm here all day if you have questions or are confused. Okay, I'm not really sure how we might have questions on this, but here we go.
I've seen pee on the wall before.
That's disgusting.
I've seen poop on the
Okay, so in here, we were kind of all over the board. Adding and subtracting, though, a lot of us are coming with a lot of background knowledge on adding and subtracting. So I have decided to take topic 2, which is our fraction unit, and split it into 2 smaller units. So we're going to do adding and subtracting with a focus on a word problem strategy, and then we'll take a summative, and then we'll move into multiplying and dividing. Reason being is that will make your summative a lot shorter and more manageable. It'll be less that you have to know for each summative. So we likely are going to do a pretty quick adding and subtracting just in the next couple of days, and towards the end of next week we'll take a short summative on that, and then we'll shift gears into multiplying and dividing. Okay, so before we get into adding and subtracting, we do need to have some background knowledge on equivalent fractions. Who can tell us, this is going to be a real speed review here, what is, put it in your own words, what's an equivalent fraction? Miriam.
It's an equivalent fraction is like, so for example, 2/3 and 4/6. It's one of those. It's one of 4/6 has more, but it's shaded, so it's equal to 2/3.
So it has more pieces, but the value of the fraction is the same. So we're splitting it into smaller pieces, but they have the same value. So 1/2 is the same as 2/4 and 4/8. They all are equivalent, but we're splitting them into smaller pieces. Why do we need, or what do we use equivalent fractions for? Gus?
We use equivalent fractions to like add fractions and mixed numbers and subtract and multiply and divide mixed fractions for different uses, but it's easier to do so with the same, if they have the same denominator, and it's easier to solve the problem than to just like actually solve the problem with like, I don't know, like 4/9 and 3/6 or something.
Yeah, so when we're adding and subtracting, we need that common denominator, so we find those equivalent fractions in order to add and subtract them. But I do agree, if I look at these 3 on the bottom, these 3 are all equivalent fractions. Which one of those do you think is going to be the easiest fraction to work with? Blake, I saw you kind of whisper it. A fourth. The smaller numbers are going to be the easiest to work with, which is why we simplify our fractions when we can, because it gives us simpler and easier numbers to add, subtract, multiply, and divide. Okay? So, if we're trying to find equivalent fractions, say we're simplifying, or we're trying to get a common denominator. To do that, we're just going to multiply or divide our numerator and our denominator. We know when I say numerator, I mean top number. Yes. Denominator is the bottom one. We're going to multiply or divide by the same thing. So here, if I have 4/6, sorry, not 4/6. If I have 4 over something equals 16 over 24, I need to figure out what did I multiply or divide by to get the equivalent version. Weston? Do we multiply or divide by 6? 4. So 16 divided by 4 gives us 4, which means I can take 24 divided by 4 to give us, I think that's what you're getting at. It should be 4/6. Okay? What about for this one though? 5/8 is equivalent to 15 what? What should we multiply by, Liv? 3. So 5 times 3 gives me 15. So 8 times 3? 24. Keep in mind what that means. That means that the fraction 5/8 and the fraction 15/24 have the same value. They represent the same amount. The one that's 24ths, though, is just split into smaller pieces, and there's more of those pieces shaded. Okay? What about for this one? 7/12 equals what over 60? What do we multiply or divide by to get from 12 to 60?
5.
Times 5. So we're going to do the same up top. 7 times 5 gives us
35.
35. Perfect. Okay, we're going to use that skill as finding common denominators. So this is the first page of your notes. We're going to fill this in and write in the examples. So the first step when we're adding fractions and mixed numbers is to find a common denominator. To figure out that common denominator, we basically have to ask ourselves, what is a common multiple of our current denominators? So what do 5 and 3 both go into? Ella, I saw your hand first. 15. So what we've got to ask ourselves is to get from fifths to 15, what do we need to multiply by?
3.
So we're going to multiply our top and bottom by 3 here. And to get from thirds to 15ths, what do we need to multiply that second fraction by? 5. So I'm going to rewrite this, and I'm going to make it times 3 here is going to be 12/15. 5 and 12/15. Plus, we're going to multiply this one by 5, 9 and 5/15. You should be writing this into your notes as well. Yes, Chase?
And since it's double-sided, I accidentally glued it on the wrong way, and I tried taking it off, but then
All right. So you do need to make sure that you are showing your work and writing these things down as you're working through these fractions. So we've got our common denominator. Now we can add them. When I'm adding and subtracting fractions, I'm going to zoom this out a little bit. The best way to do this is to stack them. Instead of writing them side to side, I would rewrite it and stack them. So I'm going to rewrite this as 5 and 12/15 plus 9 and 5/15. Bless you. And then I can add the fractions. When we have that common denominator, that denominator is going to stay the same. So it's going to stay 15ths. But I'm going to add our numerators. 12 plus 5 is 17. 5 plus 9 is 14. Okay, so I add my fractions and my whole numbers. But when I look at this answer, I don't love this. Can anyone explain or tell us why I don't, Josie, like that final answer? Yeah, so 17's on top of 15 and it's bigger, which means it's an improper fraction. You've talked about improper fractions, yes?
Yeah.
So we need to simplify this back. Does anyone remember how we're going to simplify that, Cammie?
17. Well, kind of the answer.
Can you what?
Kind of the answer.
Okay, tell us what you think the answer is.
15 and 2.
Okay, so Cammie says this is going to turn into 15 and 2/15. Who can explain to us how Cammie got 15 and 2/15? Let's Chase.
well, whatever the bottom one is.
Denominator. You were right. Denominator.
Whatever that is, whatever the denominator
Yeah, so one thing that I always, the way I phrase it to myself is how many times does this 15, the denominator, go into the numerator? How many 15s go into 17, which is one time? That one is one whole, which is how Cammie got to 15 here. She added the one whole to the 15 we already had. And then to get from 15 to 17, there were 2 pieces left over, which is where that numerator came from. Do you remember that process from last year? Okay, so I think at the bottom I gave you a couple more to try, yes? All right, so let's try this. We're going to start with 2 4/7 and 1 1/3. I'm going to start by just rewriting those stacked up and down, and then I'm going to work on getting a common denominator here. So to get that common denominator, I'm essentially asking myself, what's a common multiple? If I can't come up with what do 3 and 7 both go into, what's a shortcut I can take there, Ella? Yeah, multiply them together. So 3 times 7 is, so I'm going to make those both 21. All right, so up top, what do I need to multiply the one that has sevenths by to get 21? 3. So I'm going to multiply my top by 3 to give me 12 21sts. And what do I multiply the thirds by, Weston, to get 21?
7.
So 1 times 7 up top is 7.
And then it's
And we're going to add 12 21st plus 7 21st. So 12 plus 7, bless you, 19 over 21. Add your whole numbers. 2 plus 1 is?
3.
And then I always want to check at the end, can I simplify? Can 3 and 19 21st get simplified?
No.
19 is prime. So if 19 is prime, its only factors are 1 and 19. 19 doesn't go into 21, so we're done there.
And
Okay.
if it's an odd number and it's 2 apart, it's always going to be just that, because being an odd number can't be multiplied by 2.
So 2 odd numbers, 2 apart, are not divisible by anything, yes.
Any number that is 1 apart can also not be simplified.
Correct. Very good. All right, let's look at the next one. You lucky ducks, I did something that I didn't mean to on this one. Why am I saying you're lucky ducks here?
We got 2 8.
Because we've got 2 8s as our denominators, which means you don't have to find the common denominator, you just have to add. What do we get when we add these two? Raise your hand when you think you know, don't shout it out yet. What do we get when we add these two? Jonah, what do you think?
13 and 4/8.
Before you got 13 and 4/8, what did you get? I'm not saying you're wrong, but I think you simplified. So your initial adding you got 12 and 12/8, good. Which Jonah then simplified to 13 and 4/8 because he noticed there was an improper fraction in that fraction spot. So 8 went into 12 one time. He added that 1 to the 12, and there were 4 pieces left over. Love it, but we got one more step to take, Blake. 13 and a half. That 4/8 actually is divisible by 4 still. So 13 and 1/2 is our simplest form of that one. 4/8 can be simplified to 1/2.
I like 4/8.
You like 4/8? I like 1/2.
I talked to him last night.
Mm. You ran out of room?
I talked to 100.
Oh dear. You could probably do it in that margin to the left of where you glued your foldable. We only got one left. All right, last one. 6 and 4/15 plus 1 and 9/10.
6 and 4 9/10.
6 and 4/15 plus 1 and 9/10. This one has quite a few options for common denominators. You could multiply them together and make them 1/50, which is really big. What else, though, do 15 and 10 both go into that's a little bit smaller, Maeve? 10 doesn't go into 15. So I could turn them both into 5s, but if we look, to get them to 5s, like the 10 I would have to divide by 2, is 9 divisible by 2?
No.
So we can't make them smaller. I did hear somebody shout it out. 30. They can both turn into 30, which is probably going to be your easiest bet, the most manageable number. So this top one, to get to 30, what do we need to multiply the top one by?
By 2.
2, so that's going to turn into 8. I'm going to throw this iPad out the window. 8/30ths. And what do we need to multiply the bottom one by?
3.
3 to get 30. So 27/30ths is where that one is. All right, 8 plus 27. Man, I don't know how to count that high. Can somebody help? 30 what? Not 32. 35. 7 and 35/30ths. What is the simplest form? 8 and 5/30ths. I would agree that 8 and 5/30ths is simplified, but it's not the simplest form yet. 5/30ths are both divisible by, Elliot? 8 and 1/6. They're both divisible by 5. Very good. Both divisible by 5. Questions on that one? Nope, we're not doing subtraction today. So what you are going to do, though, is you're going to flip to the cubes page that we glued in, and we're going to look at word problems real quick, and then you're going to have time to start your homework. Paper. All right. I'm going to wait until people stop having side conversations because there's still a lot of chatter happening. Some of you like to hear yourselves talk, I think. I like to hear you talk too when it's appropriate. Okay. So one of the things that we're going to work on this year, how many of you feel like when you do word problems in math, that's the hardest part of the math that you do? So if you have a whole set of problems, the word problems are the trickiest. Okay? I would say that the majority of people feel that way. Not everyone, but most people feel that way. And it's normal to feel that way because it's one thing to learn a process. Okay, to add fractions, I get a common denominator, I add, I simplify. And to just repeat that practice or that process. But when you have a word problem, now you have a whole scenario, and you have to read it, you have to analyze it, you got to figure out what problem you even set up to do it, then you got to solve the problem right, and make sure it makes sense. So there's just a lot more steps and there's a lot more analysis happening. One thing I noticed on your first summatives is that a lot of us are struggling with even figuring out what the question is asking and making sure we're answering all of the parts. So we're going to focus on a process called cubes for word problems, which is a process I want you to get in the habit of using with word problems, because what it's going to make you do is it's going to make you slow down and analyze or interpret the question before you jump right in and try to start solving it. I think sometimes people read the word problem. Sometimes you don't even read the whole thing. You read it and you're like, I know what to do, and you start solving, and then you do the total wrong thing. Okay? Some of us are rushers and just want to get our work done rather than stop and think about it. So what cubes does is it makes you pump the brakes for a second and take an extra, 30 seconds to make sure you're understanding what's being asked before you start solving. So the cubes acronym stands for this. We're going to start by circling any key numbers and information. Then we're going to stop and underline the question. And on your cubes paper, I want you to add next to question, I want you to write or command. You're going to underline the question or command. Here's what I mean by that. Sometimes we ask a question. How many apples did they pick all together? But sometimes it's not phrased like a question and it's given as a command, meaning tell how many apples they picked all together. That's not a question, but it's still telling you what you have to do. So you're going to underline that part. Then you're going to go in and box in keywords. So on those little table plates in front of you, there's a section called buzzwords. There's buzzwords like sum, difference, altogether, quotient, product. Some words that help us figure out mathematically what we need to do. Same thing with our GCF and LCM word problems. We looked at words like greatest or smallest and said, ooh, that's a key word. It tells me what I'm looking for. Those are the key words you want to box in. Next, if there's any extra information, sometimes they're really mean when they write word problems and they give us a lot of extra information we don't need. Cross it out so you don't get distracted by it. And finally, you're going to solve by showing your work. So we're not asking you to do anything crazy, but this process just makes you slow down and make sure you understand everything that's there before you attack it. So let's look at this together, and we're going to cubes this problem. It probably sounds familiar because it was off your last test. So you can put your pencil down and look up here, and we're going to cubes this together. It says, Mr. Sauer is having a cookout with friends. He's going to serve hamburgers. Hamburgers are sold in packages of 6, and buns come in packages of 8. If he wants the same number of buns as hamburgers, what's the smallest number of hamburgers and buns Mr. Sauer will have? How many packages of hamburgers will he need? How many packages of buns? Show your work. And it also says that it's a 4-point problem. That's important because it tells us this is worth a lot here. We probably have multiple steps we're going to end up doing. Chase.
Circle smallest is for 1.
So I would say that smallest is a key word, so we're going to box that in. I totally agree. Here's the deal. At the end of the day, if things are circled instead of boxed or boxed instead of circled, it's not a huge deal. It's just that you're picking out that key information. So we're circling other key numbers or information. What else is important here that we're going to need to use? Blake?
Hamburgers are sold in packages of 6, and buns come in packages of 8.
So hamburgers are packs of 6, buns are packs of 8. Is there any other important numbers or information? Weston?
Well, I thought we could do the E and cubes to eliminate.
Well,
Mr. Sauer's having a cookout with friends. He's going to serve hamburgers. We don't really need that.
I agree. Let's do this in order though, okay? So that we start learning the acronym. We circled. We need to underline the question or command. Ella?
Underline, he wants to have the same number of buns and burgers.
Is that a question?
Oh no. Underline how many packages of hamburgers will need and how many packages of buns.
Okay, so there's one question. How many packages of hamburgers? Here's a second question. How many packages of buns? Are those the only questions? No, there's a third question. What should we underline? Cammie? That's not a question. It is a command, but that's actually part of our cube, so we don't need to underline that. Anaya?
What is the smallest number of hamburgers and buns Mr. Sauer will have?
That's a question that should be getting answered. What's the smallest number? So, bless you. How many? Bless you. How many of each is he going to get? So there are 3 parts to this question that should be answered when you give your response. We've already solved this one, so we're not going to solve this one today, but we're going to look at 2 more word problems and cubes them. And then I'm going to give you homework and let you start. All right, Cammie and Maeve, you're making your grand appearance in our math word problem today. Cammie picked 2 1/4 quarts of strawberries and Maeve picked 3 1/2 quarts of strawberries. If they combined their strawberries, how many quarts would they have? Tell me key numbers or information I should be circling. Ella.
If they combine their strawberries, how many quarts do they have?
So that's going to be underlined, how many quarts they have. That's our question or command. What numbers, though, should we be circling that we need to use here? Maeve. Yep, and I'm actually going to circle the label that's with those so I know what label I'm going to use for my answer. It's in quarts, okay? Are there any keywords that we should box in that might indicate, Blake, what we're going to do here? I love that word combined. Combined implies we're putting them together, so we're going to add those. Anything we need to eliminate here? Quarts is important. That's the label we're going to use. We don't want to get rid of it. Gus?
You can remove like all the strawberry labels and all the names.
I mean, we can cross out little words, but really the point of eliminating is if they throw in like Anaya picked 5 quarts of strawberries, and then it says how many if Maeve and Cammie combine their strawberries, how many do they have? And we don't care about what Anaya picked. That would be information, extra information. We're not always going to cross things out because you don't have to cross out every little word. Okay, it's just if there's extra stuff to distract us. Now we're going to solve this. 2 1/4. We said combine, so we're going to add. What's our common denominator going to be here? 4. I can't make it 2 because I can't divide the 1 to make it smaller. So I'm going to multiply by 2 here to make it 2/4. Who can add those? Ella. 5 3/4. Notice S is solve and show my work. So there's my work and answer in a complete sentence. My complete sentence could be Cammie and Maeve. If the pencil would work, that says Maeve. Can't you tell? Picked.
No, it looks like mom.
It looks like
5 3/4 quarts of strawberries.
beautiful.
On point. Looks like a 6th grader wrote it, actually, is kind of what I was thinking. All right. Let's just mark this one up and then we're going to be done. Greg's band made a CD of their hits. Oh, they've got lots of hits. The first one was 1 2/7 minutes long, and the second one is 2 4/7 minutes long. That's all their hits, 2 songs. How many minutes is the entire CD? What would I circle? What's a key number or information here? Griffin.
1 2/7.
Yep, I'm going to circle the label with it. 1 2/7 minutes. What else? Jonah.
The other one.
Yeah.
The 4/7.
2 4/7 minutes. Anything else that needs circled?
No.
What should I underline? Great. Oh, go on. How many minutes is the entire CD? Anything we need to eliminate? Not really. There's not extra information in there. I would solve. I would show my work. Add those together. Ooh, common denominator already. We probably could just add those. 3 6/7.
Can't simplify because they're
Who could phrase a sentence for what the sentence might look like there? Ella.
The whole CD will be 3 6/7 minutes long.
Yeah, what a long CD. That's crazy. Good.
Here's the